Hello. In this last video, we will analyze and design some indirect adaptive controllers. An adaptive controller can be described as a controller that can modify its response behavior when changing the dynamics of the process. So, an adaptive controller can be stated as a controller with adjustable parameters and a mechanism for adjusting the parameters. In this sixth practice, we will design an indirect self-tuning regulator for velocity and position control. The process variables will be estimated by recursive least square algorithm. There exist lot of adaptive systems, such as gain scheduling, model reference adaptive control, self-tuning regulators, and dual control. Each of them has their pros and cons, and depending on the control problem, one can suit better than another. In this project, we will develop a self-tuning regulator. In addition to this, everyone has a design procedure to satisfy some specifications. Here, we can also split the problem as direct or indirect adaptive controllers. In direct adaptive control, the control parameters are directly changed without the need of estimate some other intermediate variables. In indirect adaptive method instead, first, the process variables are estimated, and in terms of this variables the control gains are updated. As previously mentioned, in this sixth work package, we will design an indirect self-tuning regulator for velocity and position control. The estimation of the process variables will be done by the recursive least squares algorithm. The controllers have been designed by pole placement, taking the tuning equations obtained in practice 4. For the recursive least square estimation, first, our plant's model must be explained as a regression model. As we can see, the model can be explained as a multiplication of two vectors. Phi, the regression vector, where the input and output values are kept, and theta, where the variables that represent the model are kept. This last vector is the one that have to be estimated. So, the algorithm works as follows: the actual parameters are estimated by adding a correction factor to the values of the parameters estimated on the stage before. This correction factor is dependent on a correction gain matrix and the estimation error. This last one is obtained by subtracting to the actual output, the regression model designed by the parameters estimated on the stage before. Lambda, or the forgetting factor, has a very high influence when estimating the parameters. The higher the parameter, the smoother the parameter estimation, since k goes to 0. When lambda is less than 1, the estimator gain k will not go to 0 and the estimates will fluctuate. This fluctuations increase when decreasing the forgetting factor. That's why, the best option is to choose lambda equal to 1. As on the practices before, we will create an indirect adaptive control for velocity control and another one for position control. This figure shows the Simulink model designed for the adaptive IP control. As we can see, after the parameters are estimated, the controller gains are updated. It can also be analyzed that the adaptive controller is composed of two loops. The inner loop, or the system's control loop, and the outer loop, where the parameters of the regulator are updated by the estimated parameters. In this video we can see the system's behavior with the proposed adaptive IP controller. We can also analyze the system response to the application of the magnetic brake. This images show the first 5 seconds of the experiment done in the video. As we can see, at first, the parameters vary a bit, but finally they settle in a constant value. As we can see, the estimation error, although is quite noisy, it always tend to 0. Finally, this figure shows the Simulink model designed for the adaptive IPD control. As in the case before, the adaptive controller is composed of two loops. The control loop, in green, and the parameter estimation and control action update, in orange. By this video we can analyze how the parameters are estimated online and afterwards, the control action is updated. As it can be seen, in this case, the parameter converge rate is slower than in the case before, that can be directly linked with the fact that the system's order is higher in this case. This images show the experiment done in the video. As we can see, at first, the parameters vary a bit, but finally they settle in a constant value. This makes the output look different on the first pulses compared with the final ones. As we can see, the estimation error, although is quite noisy and the parameters don't converge to their real values, it always tend to 0. This is because the recursive least squares algorithm tries to minimize the error between the real output and the estimated one. This doesn't mean the parameters will tend to their real values, as the regression vector can have another values on the parameters and still make this error tend to 0.